Hello everyone, my name is Abhishek Bansal. In this video, I am going to discuss the mathematical operation of the buck converter. I am going to talk on the continuous mode, discontinuous mode and the borderline mode. Okay. So, we are having and I am going to talk on the DC to DC operation. If the input source has been derived from an AC, it can be converted to DC using a rectifier, and the mathematical operation is exactly the same of a rectifier only. So, that would be a separate video, not in this. In this video, I am assuming that we are already given a DC source. So, this is basically a buck converter where you will find an switch is connected in series with the input, and here the input is what? DC. The input is DC. Okay, plus minus V input is here, and we are having a V output here. V output here. Okay, and this V output by the name buck converter, it's always less than the input voltage. And here I am assuming the load is the given load is resistive in nature. Okay, I am representing it by RL. It means L for the load, not for the inductor. I am taking the load to be resistive. I am not taking load to be an inductive. I am neither taking a load as a capacitive. I am also neither taking the load to be an RLC. I am taking a load for the simplicity to be a pure resistive. Okay. So, we are given a switch that could be replaced by a MOSFET. You can find it can be drawn in a similar way by I can draw a MOSFET here and a diode. This is called a freewheeling diode. Okay, again an L and the C circuit, that's an LC filter. I can even draw in this manner. You can find all these mean the same thing only, thus only a difference in the drawn representations. These even by drawing it does not mean a different thing only, because it is again in series with the input in both the diagrams. So, I can now even draw this buck converter using a SPST and an SPDT. Okay. If suppose I want to draw using an SPDT, it would be this is an SPDT, and I can draw the same thing using an 2 SPST switches. Like here already I have drawn a 1 SPST. Here I can also replace it by SPST. So, what is basically happening in this circuit is that we are given a switch. I would be explaining using 2 SPST only. Okay, not an SPDT. So, what we have given is that we are having a switch that is in series with the input voltage, and during when the switch is on, when the MOSFET is on, say, or the switch is on, or the switch is in closed position, okay, this will remain in the open position only, or this diode would be set as it is in the reverse bias. So, this input source is going to feed the inductor and then output. Inductor is going to store energy and the output is going to receive energy from the input. And during this time there would be difference of the voltage between the input and output, and that is going to cause a ramp voltage in an inductor waveform. Here you will see this is a t axis, okay, this is an x axis and this is a current axis. Okay, So if I am taking an IL1 here, the peak I may draw, I denoted by IL2. So during an on time, it rises linearly upwards with the slope as difference of the voltage minus, or that is the output minus input minus output by inductance, and during an off period this switch gets open. Okay, this switch gets open and this diode becomes forward bias and gets closed, and this completes the path, and the inductor current falls down linearly with the slope of minus V naught by L. I would be driving both these equations, and in this both you would notice that this is a 0, it hasn't fallen down to the 0. The inductor current is 0, that is why it is called as continuous conduction mode, CCM. Okay. So if suppose I want to draw a, in the discontinuous mode, it falls to 0, that means in the, it rises up, it down, okay, and then it, this is a discontinuity here, again up and down. So this is a discontinuous mode. Here if you notice that I have mentioned only IL1 and IL2, but in practical scenarios you can see, you may find that these peaks are not of same, like this is lower, this is an upper. That means in a practical scenario or in a transient scenario, basically you will always find in a transient scenario that these peaks won't be same. We will have IL2, IL3, IL5, IL4, IL5, IL6, IL7, and that could be numerous like similar kind of way in the harmonics only. Excuse me. Yeah. So let us go on the operation of this buck converter. Before I explain the mathematical operation of this buck converter, there are few things that you should know. First thing is that the MOSFET or any other switch, it would be on for on and off, on and off. So this would be on time and this would be an off time, this would be an off time, and this would be again an on time, and this would be an off time. So this on time is basically the switch is closed, and this off time is basically the switch is open. So if I say the switching time period is T, and it's on for the, that means it's on for, this is a T axis again, and this is again a voltage. So this on time duration would be dt. That means the off time duration would be what? T minus dt, which is simply a 1 minus dt. The other thing that you should know, that the average or the DC component of the output voltage, it would be given by V naught equal to 1 by T, 0 to T V naught dt. Okay, and as this time for the on period I mentioned dt, so I can replace this T by dt. This, the input source is here what? V input, I can replace it by V input for an on period. Okay, so what do I get? V input d 1 by T definitely here, and minus V input into 0. Okay, and this becomes what? V input d, so this would be dt because I have taken a dt. Okay, 1 by T, and this tt will get cancelled, it would become V input d. So the output to the input relation is this thing only, and the transfer function we can very easily say V output is basically V input times the duty cycle. This is the main equation for the buck converter, and we will similarly derive the similar kind of equation for the boost and the buck boost and the chook and the other converters also. The other thing you should know that this this duty cycle consists of what? It is the ratio of the on period and the total time period. The total T is here was T on plus T off. Okay, and we know 1 by T is the frequency. So the duty cycle becomes, this implies duty cycle is equal to T on times the switching frequency, because with the switching frequency only we are going to switch on and off the MOSFET. Now before analyzing it, we make several kind of assumptions in this. If you recall from the video of the volt second balance, you would notice that I have mentioned that one thing I didn't mention there, but it's similar to that only, that if we taking suppose any, because in this analysis we are going to assume that we are having a periodicity is, this circuit is following periodicity, that means the inductor current is periodic. When I am saying the inductor current is periodic, what it means? The inductor current is IL. When I am saying it's periodic with a time period T, suppose I say the T, it means IL T naught plus T would be equal to IL T naught. Okay. So this is what the periodicity means by definition, and if I am writing T, it means it is the IL T only. Okay. The other thing is that the average current, I am talking of the average current or the average inductor voltage or the average capacitive current. I am talking, let us first take the inductor voltage. The average inductor voltage would be 0, that means the VL would be 1 by T. Now here what I have taken, T plus T naught, sorry, T plus T, I am taking T plus T, and let us put V tau d tau, and this would be equal to 0, the average would be equal to 0. Okay. Why this would be equal to 0? I have explained it, because it is going to follow the voltage second balance principle. Because of that only this would be equal to 0. If you recall in the from the first video, if you from the voltage second balance, I have mentioned it like something like this way. If the inductor has some initial current also, I have mentioned it this way. Zero minus. Okay. Now since I am explaining using a periodicity here or the period here, I can put this T naught plus T, and instead of 0 minus I am simply putting T naught. So this means that if I am going to take this here on the right hand side, it will become T naught plus this T minus IL, this would be again an IL only, or T naught is equal to 1 by L, this would be T naught, not 0 here, because I have taken T naught here, T naught plus T VL dt, and this would be equal to 0. If you remember from that video, I mentioned that the starting and the ending values are the same, because they would be same only because they are the periodic currents, or I have said that the steady state in that this I have mentioned it like this way: IT minus I0. Excuse me. Okay, so similarly we can find the capacitive charging balance. Here I have taken an average inductor current. Similarly we can take an average capacitive current. Okay, so the average capacitive current would apply same thing, average capacitive voltage T naught plus T, it would be equal to 1 by C, and it is going to equal from T naught, periodicity I am taking T naught plus T, okay, and this would be definitely the current only across current through the capacitor. So it is an IC T dt plus voltage at voltage at T0. Okay. Similarly, I can take this V at T naught here only, that means V naught T naught plus T minus V of the T naught. Now according to the capacitor charge balancing, this would be equal to 0, that means this whole integral would be 0 only. Okay. So it means the capacitor voltage is periodic. The stored energy is going to be same at the end of the period. That means the average power that is going to be absorbed by the capacitor is going to be 0 for the steady state periodic operation. That means I can say the energy absorbed would be 0. Okay. So we can write this average, because we have to note that I am talking of an average. So sometimes it is written as by this way, ICT, or sometimes they write AVG, ICT. Okay. Similarly, I can draw say for the inductor, the voltage is average voltage across T. So this would be equal to 0, this would be also equal to 0, and using these principles I am going to design the equivalent circuit, DC circuit, and we are going to analyze this buck converter. There would be more assumptions in this. The first one I have already mentioned, that this current has to be periodic, this two must be followed, the Volts-second balance and the capacitor charging balance. The other thing that I am taking is that there is no power loss here. That means I am taking a that the input voltage, sorry, the input power is equal to output power. Practically, and even the if you are considering non-linearities, this output power would be accompanied with the losses. But here we are not taking any loss, we are assuming losses are equal to 0, we are taking the ideal scenario, P input is equal to P output. The other assumptions that I am going to take is that the circuit is operating in a steady state. As now I am talking of a continuous conduction mode, the inductor current has to be continuous. One has to make sure that it is in the continuous mode only. And the other assumption is the capacitor. If you would notice that in the circuit of the buck converter, I have mentioned here a freewheeling diode. This was I have talked upon L, I have not talked upon C yet, and I have talked upon the load. So, the input on period, this is going to store energy and it is going to fit an output also. Now, this capacitor has to be large enough to maintain the output voltage at a constant level. Okay. Theoretically, we can assume it is a very large capacitor, but practically this capacitance would be having certain kind of value. Okay. So, let us assume that our switch is closed, that means this is an open, this is open, our switch is basically now closed. So, what is happening? We is saying that the voltage across the capacitor or voltage across the inductor VL is equal to what? V input minus V output, and we have already stated that this is going to equal to L di by dt. That means, if we are going to take L here, we can say V input minus V output by L is equal to di by dt. So, if you remember, I have mentioned that in the waveform I have mentioned this is the this is a waveform and the slope is basically V input minus V output by L, that is basically because the rate of change of current. You can see even from here it is the rate of change of current. Now, the derivative here it is a positive, it can be negative also, but here in this scenario when the switch is on, it is a positive derivative. So, that means the positive derivative is there, the slope is increasing or the current is increasing, which we can see here. We can write it as delta IL upon delta T. Okay. We know this is here the time duration is what? dt. The switch is on for the period of dt. So, this equation we can rearrange it as, and we can say very safely that delta IL is equal to V input minus V output upon L into dt. So, this is one equation we have got. The inductor, we have considered the inductor current here. Okay. Now, at the time of so this at the time of switch off, when the switch is off, then we will say, we will notice that it is a VL is equal to minus VO, similarly it is an L di by dt. Okay. Because the diode is going to be forward biased, and that means here if I take an L here, the rate of change of current or the slope is negative. As the slope is negative, it means it is decreasing, the current is decreasing, and the slope value is minus V naught by L. Similarly, if I can put it as a delta IL here, delta IL upon delta T. Now, here what is T? It was 1 minus dt. Okay, remember I have shown it here that it was dt and it was t, and this time duration is 1 minus dt. So, this is an IL2 or this is an IL1, and we can say that the difference is basically what? Delta IL. Okay, this is an inductor current. Both these equations of during the on and off time would be used. Okay. And we will see that the voltage across the inductor would be like this way only. Okay. So, one assumption that I made in the beginning, that this buck converter is operating in a steady state. So what it will mean that the inductor current is going to be at the end. The inductor current at here, it's not 0, it's continuous only. Okay, the inductor current at the end of the cycle is same has to be at the beginning of the cycle. That means if I am going to add them, if I am going to take an IL during an on time, and if I am going to take the inductor current during an off time, they have to be equal to 0 because of my assumption steady state operation. Now if I am going to put the values which I have just derived in these equations, I would get V input minus V output upon L dt minus V input upon L 1 minus d t, and this is equal to 0. Okay. So we can solve very easily for the V naught. I just draw it. This L it will go. That means we are going to we would be left with the V input minus V output dt minus V input 1 minus d t. This tt will also go. Now we are left with V input d minus V output d. I am expanding it here only, minus V input plus V output d, and that is equal to 0. This again will cancel. So we are left with only two things. We are left with two things. V input d is equal to minus V output equal to 0, or we can say V input equal to this V output voltage this. So this is the relation that I have talked in the beginning. This is the input to an output relation of a buck converter, and we have just derived it. Okay. So it will means that an output voltage is depending upon the input voltage and the duty ratio. So if an input voltage is fluctuating, the output voltage can be regulated. How we can regulate it? By adjusting the duty cycle. Okay, it's generally a less than 1. Okay, I will come to that later on. Okay. So this thing would be achieved using a feedback loop. That means when I am going to take an example of an buck converter design example, I will explain that time. So I have mentioned that I am taking the load to be resistive. Now as our because of that, the average inductor current, if you remember, I have talked of an average inductor current, that would be then same as an average inductor current would be same as average load current or the average current in the load. We are taking here simplicity for a resistor, so it's a resistive load. Okay, that means IL would be equal to an IR, and as an output voltage by, it becomes the simplicity. I have mentioned it there, RL here. Now we know that we have derived delta IL during an on and an off period, both we have derived. Now we can find the minimum and the maximum values based on these equations. We will say that then I max is basically an IL plus delta IL upon 2. Similarly, the minimum value of inductance we can find IL minus delta IL upon 2. Okay. So here this minus during this here IL is for the during the off time I have taken, and this here IL I am taking during the again an off time only. Okay. So if I am going to put it here, we can say IL VL now, it is V naught by L. Now let me take one by one, because just remember one is the plus sign and the other is the minus sign. So this will become V naught by R, and we know that a delta L, I have derived it as V naught upon L 1 minus D T, okay. And if I am going to take a V naught common here, it will become 1 by R plus V naught I have taken, so 1 by 2L 1 minus D. V naught T is what? Time period, or T is also equal to 1 by F, so it would be 1 by LF. This is the I maximum value of an inductance. Now I can similarly get a minimum value of an inductance. Here again I am going to put VL as V naught by R minus sign because of this, and we are going to take 1 by 2 and V naught upon L 1 minus D T. Okay. Again I am going to take a V naught common here. We are going to get 1 by R minus 1 by 2L. Again we have the 1 minus D, and similarly in this manner I can replace the T by switching frequency 1 by F, and I got this thing. So this is basically the change in the inductor current we know. And from the change of an inductor current delta IL, you would notice that I have taken a positive sign here, not negative sign here, because we are talking of the change of the inductor current. It is the change of the inductor current. So what these equations should be valid, or the assumptions should be there. That means the inductor current is continuous, it is a steady state operation, it is a periodic operation. The steady state operation is going to make the final and the inductor current value at the beginning of the cycle to be the same at the end of the cycle to be same at the beginning of the cycle. So now we knows this is the continuous mode operation. That means now to avoid, so we should also know what is during the boundary conduction mode, this I minimum would be equal to 0. That would make it, if this I minimum is equal to 0, it is going to make a boundary between the continuous to discontinuous, because the current I have mentioned, that a current I have mentioned in the continuous mode I have mentioned it's this way, and in a discontinuous mode it's coming to 0 and then rising down. So it means if the I minimum goes to 0, this will define the boundary conduction mode from the continuous to discontinuous mode. Now let us again put it 0 and solve this. We will find, we know that this is equal to V naught 1 by R, I have just derived in the last slide, 1 minus D upon 2 LF one minus D, and rearranging it, this is equal to 0, this cannot be 0. So 1 minus R, this is will equal to 0, or we will say that 1 minus R equal to this thing, okay. And if I am going to rearrange it, I can take this L is not an L and F are together, not the subscript. So LF, I am talking of a minimum, and equal to R will go here, D will remain here, 1 minus D R. So the boundary conduction mode I minimum equal to 0 give us this LF minimum value, and it also defines that this minimum value of inductance should be there, this switching frequency, minimum switching frequency should be there at which you are going to make your converter run to avoid going it into the discontinuous mode. So this is again a boundary line condition, this much for the continuous current, for a continuous conduction mode we are getting the what should be the minimum value, theoretical value of the inductance and the switching frequency that we should use in the circuit to make it work in the continuous conduction mode. Okay. So this is a minimum value, but I can use value which is greater than that, than this theoretical value. Now the other thing that we can take into account is that the peak to peak variation in the inductor current. So the peak to peak variation can be also studied using the same delta IL, and then these only equations. The one thing that I want to mention firstly is that what is basically where you are going to use much in the okay, I will come that to later on. Continuous or discontinuous mode, continuous or discontinuous I will come later on, because when the low current is drawn, that means we are using a discontinuous mode, and in an higher current levels, if we circuit needs an higher current level, we are operating it in the continuous mode. So let us first do this variation of the peak to peak variation in the inductor current. Okay. So peak to peak variation of inductor current can be, we know the delta IL equal to V input minus V output upon L into dt, D sorry capital dt. Okay. And if I am going to replace this T by 1 by F, it would become L F. Okay. And if I am going to, I can we know that V output is equal to V input D. So I can write this equation in terms of V input also or V output also. Let us say if I am going to write it in terms of V input. So V input D upon LF into D, or in this way would be V input 1 minus D upon LF. If I am going to write in terms of V output, V input we know V output by D minus V output D upon LF, and this will become V output minus D V output, this D and then this D will get cancelled upon LF, or V output 1 minus D by LF. Okay. So this is we can get here, or let us take it an output only instead of the input current. it would become what? If I this is basically equal to delta IL. So let's rearrange it. Put L here, which means V input minus V output upon delta IL F into D, or in terms of V naught, what would be 1 minus D delta ILF. Okay, delta ILF. Okay. Now we have, last thing is that we have assumed all the conditions to be ideal. I have mentioned that there is no power loss. P input is equal to P output. What P input means? V input, I input equal to V output, I output. And if I am going to rearrange it, we will find V output by V input, I have taken this in here, equal to I input by I output. And if we say this is basically a voltage current relationship of a DC transformer or a transformer in basically in an AC applications, this relationship is basically used in transformer of an AC applications, you would notice that. And because of this only, buck converter is set as, the buck converter is equivalent to a DC transformer, because this satisfies the equation relation of the transformer in AC applications. Okay. Now I have talked of the inductor voltage, I have talked on the inductor current. One thing which is missing is the capacitance. I mentioned that the capacitance value have to be large to maintain and regulated output voltage. Okay, now let us see the waveform of the I versus T. The capacitor current is this way, this would be T axis, this complete would be T axis, it would be this way, and the difference in these two would be delta I L only. Okay, these two difference would be delta I L only. This is important, it is not mentioned, I am not mentioning here, it is a delta IC. I am talking about the capacitor. Okay. Now if I am taking an output voltage ripple, okay, I have mentioned, we know that the capacitor has to be large to maintain an output voltage, but there would be variation in an output voltage, and hence there would be variation in the ripple. And if we know that, we can see this was our buck converter circuit, current was flowing, I was in this direction, this was an inductor, this was capacitor, this was the load. Okay, this was the load. So the load was going here IL, it would let's put it at IR, because it would be an inductor load. IL is the inductive current, this is the current flowing through the load is IR, the current is an IC. So through the node equation we can very well calculate that IC is equal to IL minus IR. The other thing is that we know that when the capacitor current is positive, here the current is going to positive, here it is in negative. So when it is going to be positive, that means the capacitor is charging, and we know that the capacitance formula, we know that Q is equal to CV. Okay, let us put the CV naught. So delta Q would be equal to C delta V naught, or delta V naught would be equal to delta Q by C. So this delta Q is what? This delta Q is what? This is the delta Q we are talking of. So this delta Q is basically the area of the triangle. Okay, and it's the above of the time axis we are talking of. Now the area of a triangle we know, half into base into height. We see that this base is basically t by 2, and from here to here we are taking it as delta L. I have already mentioned just in the last slide, it's a delta IL. Therefore, this delta Q would become, the area of the triangle would become half into t by 2 into delta IL upon 2. The delta IL is from here to here, not here. And if I am going to, this would be T delta IL 2 into 2 into 2, it's an 8. And if we are going to put this delta in this Q value in this, we will get delta V naught equal to by 8C. Okay. And obviously the ripple voltage, we will find the voltage would be like this way. Here this was the current and this was the voltage, and this is the ripple voltage, capacitor ripple voltage, and here V naught is the ripple voltage, not an output voltage. So where here we have got delta V naught, T delta L value we can put. What was delta L value we have got? We were using V naught by L 1 minus d T. This delta L value we have used in you would notice that in finding the minimum and the maximum value, we have taken this value of the delta IL. Okay, this was, if I put a minus sign here, it would become delta IL during an off period of time. So this T I can again write in terms of frequency, switching frequency. It will become LF here, and this T is also here. We can again put F here, so it would F square. That means this delta V naught is not an output voltage, it's a peak to peak ripple voltage at the output. That's why I mentioned delta V naught, because it's a peak to peak ripple voltage at output. Okay, so it would be V naught delta, from this we can say it's a V naught 1 minus d upon 8 LC F square, and we can take this V naught here, we can say delta V naught by upon V naught is equal to 1 minus d, this thing. That means we are expressing the ripple voltage as the fraction of the output voltage. And if I just rearrange, we can find the value of the capacitance from here, that should be the capacitance. Okay, we can find the value of the capacitance required. Okay, just take C here and put this complete equation here, this complete RHS, take it here and C here, we will find the capacitance value. So now let's talk of the discontinuous mode. I have completed the conduction mode. I have taken the boundary condition, okay, and let's take on the discontinuous mode. In the discontinuous mode, we know the inductor current has to be, or the inductor current is not continuous. So what would be the input and an output voltage relationship? We have find out V output is equal to V input D. This was the relation valid for a continuous conduction mode. Now, since there is a discontinuity, we have talk of an on time, we have talk on an off time, we have talk on an on time, and in that we were talking of the continuous, the inductor current never reaches 0. It was always like this way. So if I take a again we are talking of here a periodic operation only, okay. That means I am talking it what now. So what is basically happening now? I have already mentioned the graph is like this way. There is discontinuity. So this we have already mentioned that this would be T, this was T, this was dt, okay. That means our dt is here, and from here to here it's a d1t. This is the d1t. Excuse me. So and the other difference that it's going to make is that I have talked I have said that the inductor voltage was what? The inductor voltage I have drawn this. Let me draw straight lines only, because it would be a straight line I have taken. These are all straight lines, okay. So this is what this peak is what? V input minus V output, and this was for the conduction mode, okay. So in the discontinuous mode, there will be difference in this. It won't be direct here. Here it will, let me draw a separate only. In the discontinuous mode, it would be this discontinuity I will get this way, and this is a dt. This would be again similar V input minus V output only, and this difference is the d1t. So that is an inductor current, and sorry, that was an inductor voltage, this was an inductor current, and what we basically getting an input and output relationship for a periodic operation, because we are again assuming the same thing, volt second balance and the periodic relation. V getting V input minus V output dt minus V output d1t equal to 0, okay. And if I am going to rearrange it, that means I am going to expand it, and when I am going to expand it, we can say this tt will get cancelled and this will become equal to Okay. Okay, one thing I forgot to mention is that in discontinuous mode, if I am taking this thing, this was V naught and it's a minus V naught, and this rest I have explained it. So this was the discontinuous mode operation. Let's expand it more. This mathematically, we will find that we are going to have here, if I want in terms of V input and V output, I can say V input D equal to V output D plus V input D, or we can say very easily V output upon V input is equal to D upon D plus D1. That means the inductor current, average inductor current, again I am going to talk of an average only. The average inductor current is going to equal the average resistive current, and that is going to happen because an average current through the capacitor is 0. And when we are taking an output voltage to be a constant, that means IL is equal to IR is equal to V naught by R, and we can compute an average inductor current from the graph itself. Okay. So if I am going to take a graph again, let me draw the graph again. We will say that this is an IL. Okay, this I am taking dt here. This I am taking d1t. This I am taking a t. This I am taking an I max. Okay, and if I am going to do the source current, this would be the source, because the source is going to get, that means the input current, if I am going to talk on the input current, it would be this. So this is dt, this is t, this is an I max. Here it's an inductor current I L, here it's an input current. Okay, we can compute the inductor current. We can say an IL here is what? 1 by T half I max into dt plus half I max into d1t, because we are having here not divide this thing. We have two triangles here. This triangle I have, and I have this triangle. Okay. So it's very simple again. This is the same formula. This is equal to what? 1 by 2. We see that t, all the t's will get cancelled. I max I am going to take common, and we have simply d plus d1. So this is the basically an average inductor current. This is the average inductor current is this thing. And I mentioned that an average inductor current is going to equal to the average load current. Here the average load is the resistor, so it is going to be a average resistor current, because the current through the capacitor, the average current through the capacitor is 0, and this would be equal to then what? IO, load we are taking, that is basically the V naught by R. So, since the current starts at 0, the maximum current is the same as the change in the current over the time when the switch is closed. So, when the switch is closed, the voltage across the inductor is what? V input minus V output, and we can very easily say this is basically equal to what? L di by dt. Again, if I am going to take it in that manner, that means I am going to get a V input minus V output, because remember that when the switch is on, this was the inductor voltage, it was applied in the forward direction. So, this would be same again, but here the difference comes what? It is a discontinuous, and the other thing is that again this would be dt only, like in the previous section, but here delta IL is then I max. Okay. Now, we can solve for an I max. We can say I max is equal to delta IL that I have taken, and that is equal to, I can take this dt here this side. This is an I max. Remember that I mentioned that I max 1 by 2 I max d plus d1 equal to V naught by R, and this is basically what? This was basically what? Average inductor current IL. So, this is here. So, we can, instead of this V input, we have to put in terms of V output only, and this would be equal to, then I max would be equal to V naught d1 T upon L. Okay. So, equal to what? Equal to, this would be equal to what? V naught by R only, let us put V naught by R only, but this would be equal to half V naught d1 T upon L and d plus d1. That means 1 by 2 will get cancelled. If I am going to take it here, d plus or rather if I just going to expand it here, this thing only, 1 by 2 V naught d1 T d by L plus V naught d1 square T by L. Okay, this we can easily get, and this would be equal to 0. That means this V naught we can take common, V naught will get eliminated, T will also get eliminated. We are left with what? 0 equal to half d1 d upon L plus d1 square upon L, or this would be 2L, this would be 2L. Okay, so that means d1 square plus d1 minus 2L by RT. I have done a mistake in the last step somewhere. This equation would come to be this thing, it won't be equal to 0, otherwise this will be get eliminated. This would be equal to 0. Okay. The mistake was, let's rectify the mistake only. We have got an expression half of an I max d plus d1. This was the average inductor current that we have got, and this is equal to 1 by 2 V naught d1t upon L d plus d1 equal to V naught by R. It was not equal to 0, it was equal to V naught by R. That's why I have cancelled the V naught. So we have to take these two equations and then solve it. So what we have got? V naught will get cancelled. I have got half d1 t by L d plus d1 1 by R. Okay. Okay. The last step, in the previous slide I have done mistake. I have put equal to 0. It was not equal to 0. It was equal to V naught by R, and there was no t. T would remain in the equation. So we got d1 t d, or I just put an RT here, and 2L I take it here. So we are left with d1 d plus d1 equal to 2L by RT, and if we can expand it, d1 square plus d1 d minus 2L by RT. Now we have a quadratic equation. Okay, and we can solve it for the d1 very easily. We can say d1 equal to what? Minus d plus minus, the discriminant would be d square plus 8L by RT upon 2. Now we know that in the case of discontinuous mode, I have designed it's a V input d upon d plus d1. So we can put the value of d1 from here. Okay. Therefore we can say when the boundary conduction mode occurring, the boundary conduction mode is basically a transition from continuous to discontinuous, or a discontinuous to continuous. One thing is that we are designing the converter particularly in the continuous mode. I have already mentioned that the converter is going to operate in the DCM if the low current is being drawn, but if the load is not fixed, the load is variable. Suppose it is going to have a higher current, it is going to operate in the continuous mode at higher current levels, and the transition, the boundary, that means it's going to be divided by d1 is equal to 1 minus d, because in that sense it would be 1 only, and we will say it is becoming a continuous mode. So that is basically the three modes of operation: continuous mode, discontinuous mode, and a boundary continuous mode, the boundary condition. Okay, thank you.